All right, welcome. So I had to be reminded that we had to have a test 2 at some point. And so I thought, oh, shoot, okay. So I had the days kind of laid out, and we are going to cover chapter 3 and 4. We're not going to go crazy deep. For example, I'm not going to get into, 3.5 that much. We're just going to touch on it and then get out. But I encourage you to read it on your own, because it is valuable. But the textbook does a really good job of explaining things. And so I just want to talk about the general concepts in chapter 3 and chapter 4 before the end of the term. So what I've decided to do, and hopefully you guys are okay with it, is I'm cutting the classification lab because you have the material. You can do the lab if you want to, but I'm not going to assign it. I can do something like make it a bonus lab, but I think everyone's kind of busy right now. So I think we'll just cut that lab and then use that lab time potentially for you to do test 2. So what I'm going to do for test 2 is I'm going to build a Moodle quiz. Okay, so it's just going to be from the new textbook. So test number 2 will be from the material covered in the new textbook, which is that ISLR textbook. Oh, that's an R, it's an S. Okay. So basically chapter 1, 2, 3, 4. Chapters 1 through 4. Okay. And so it'll be a wrap up of everything. What I want to do is I'll make it a timed Moodle test, and nothing crazy, multiple choice questions, which means I have to try to make some assignment questions, which I don't know. This course is just beating me across the back of the head. It feels like, okay, trying to stay on top of it, and then I just keep forgetting stuff. I don't know. And like you, I'm sure this term is like insane. So not really an excuse, but it is. And so anyways, I'll make up some Moodle questions because you guys have worked hard enough. Okay, so it'll be material covered in the new textbook, chapter 1 through 4, and it'll be a timed 50-minute Moodle quiz. Oh, I guess Moodle's a name. Moodle quiz available all day on Friday. So if you want, I can make it available for longer, but I do want you to have kind of the weekend, because it's potentially your last day of classes, unless you have Monday classes. Then we have classes on Monday. And I think some people are taking advantage of the Tuesday and having random classes on Tuesday. We're not. I'm not personally, but some people might be. And so I want to have it just done on the Friday, but if you really, really need to have it open for longer, I can do that. But for now, I just want to keep it open all day on Friday. So open from, let's say, I don't know, 7 o'clock to 11:59 on Monday, or sorry, on Monday, no, on Friday. Okay, so you can use the lab time. That's why I'm making it a 50-minute timed quiz, because you do have that lab time blocked off. But of course, if you don't want to do that, if you've got other stuff going on and it doesn't work, whatever, you can do it at any time on the Friday between 7 and midnight. Okay. I guess I could have it open. Just seems weird to open it earlier than 7. Even 7's like wake up and do a timed quiz. No thanks. But I guess you can. So it's going to be a timed 50-minute Moodle quiz open from 7 to 11:59 on Friday. And so you could use your lab time to do the quiz if you want to. Okay. Okay. Any questions about the test? We can call it a quiz if you want. I think it's only worth like 15% of your grade. Nothing crazy. But then the final exam, so the reason I wanted to have it kind of at the end is, well, things got weird, first of all, but also the final exam is basically just a mashup of test 1 and test 2. So, so you'll have seen everything and there's nothing new on the final exam. Oh yeah, so a practice test for test 2. I'll see what I can do. Yeah, I usually like to have practice questions just so you know what to expect. So yes, I'm ready to commit to that. I'll post a practice test. So I will make a practice test. And how about this? I'll make it as an assignment. How about that? And it will count as an assignment. I'll make it a Moodle quiz so that it's similar in structure, and then you know what to expect. Okay. I have not even thought about making it. I just decided I would make a Moodle quiz, and that's all I've done so far on it. So I guess we'll see what happens, what I pull off. So, all right. So let's see here. Any other questions about test number 2? Potentially, I mean, final exam too, but like I said, the final exam will just be a mashup, weird mashup of test 1 and test 2. Okay. So I will post more details about the final exam probably next week because it's coming up soon. But it's just a mashup of test 1 and test 2. Oh, I see my microphone is way off. I don't think it actually makes a difference though. It picks up on my voice pretty well, but okay. So kind of end that there. So what we were talking about regression, and probably in Stat 230, you've probably seen simple linear regression, right? Where we had just one predictor variable. Now we're moving to multiple linear regression. So section 3.2 is on multiple linear regression. And there are kind of more powerful things that we can do, but multiple linear regression is very flexible and it can handle a lot of different situations. Okay, so I just want to kind of show them to you, and then in the, oh, that's what I wanted to ask. Did you guys, how was the lab? I didn't make that video, obviously. One of the authors made the videos, but I looked at it and I didn't watch the entire thing. I just kind of flipped through it sort of, but I thought 14 minutes to do that lab. It would take me the full hour to talk about all the ins and outs. And so that's why I opted to post that, but also because I didn't really have time to make my own video. And I'm tempted to, if they can kind of cram everything into a shorter amount of time because I'm so blabby, then maybe that's a good thing. So I'm thinking about just having you do, I mean, you can just read the instructions. You don't have to watch the videos. You can just read the lab 3 or the chapter 3 lab instructions. And then I think we'll do question 10 again. I was flipping through them earlier, but I'll have to decide. But okay, so that's what I'm thinking for the lab for tomorrow, which will be our last lab. Maybe I'll make a note of that here. Lab tomorrow will be our last lab. Okay. Oh, you can't find the video. Didn't I post the video? I'm not even going to comment on your last one. No. Oh, you found the video. Okay. I don't think I'm following. I know the lab 3. So then you might have to read the instructions, right? It's possible that they're kind of skipping some stuff. And some stuff you might have to get jiggy with. But I liked question 10. Maybe there's a specific part that I kind of glossed over that I'll have to, is there a specific? I know you have. I knew it. I knew it. So yeah, if there's a specific part in question 10, I can have a look at that. R is hard, so don't worry about that. But yeah, we can figure that out. So lab tomorrow will be our last lab. And what I want you to do is read the chapter 3 lab. Oops. And I'll say and or watch the video, which I'll post. And answer the question that I post. I haven't picked one, and maybe I should. Sounds like I need to be more careful picking questions, although I felt like I had it under control, but maybe not. So I'll review the one from chapter 2, and then I'll see if I can pick a good, reasonable one for chapter 3, since we're not looking at all the possible options. Okay. Oh, nice. Just a direct message here. So the Success Center does have a person that can help with R. So that's really nice. So that's worth checking out. Yeah. Okay, nice. Okay, so multiple linear regression. The multiple here refers to more than one predictor. Okay, so more than one predictor, right? Or X. right? So now we're going to have X1, X2, X3, X4. And we looked at last day, we looked at the problem becomes, okay, well, we can't actually visualize anything that's more than 2 predictors, right? And so we kind of are in the dark about what things look like, but it still works, right? And so we can have, we can visualize with 2 predictors, and often, you know, that's what we're dealing with. So we can have more than 2, but sometimes we can kind of whittle it down to 2 predictors, and that's good. But we're not expecting a visualization here. Let me just see if I can grab right, and so wait. Okay, so the difficult part with multiple regression, with multiple linear regression, is that we can only visualize up to 2 predictors. We can only visualize up to 2 predictors. Okay. So here, right, we have X1 and we have X2, and then we have our Y. Okay. Although, so, but we can still build models with more than 2 predictors. Okay. But we can still build models with more than 2 predictors. Okay. So in fact, we can have P predictors if we want to, right? And so what we have is we're going to have a model where we have beta naught plus beta 1 x1 plus beta 2 x2 plus all the way up to beta p xp plus some error term. Okay. So this is allowing for P predictors. Okay. And when they're being added linearly like this, that's what makes them a linear model. Okay, so when we're just adding terms together, then we have a linear model. Adding terms together makes the model linear. Okay. Just to kind of clarify, what does it mean? Because I know when I was starting out, I was so confused. You know, we're talking about a linear model, and yeah, of course, that's a straight line, but now I have I have multiple predictors, and it just doesn't sit well, right? And so the linear part is that they're being added in linearly. Okay. So our prediction, right, our model then is going to be y hat, and I'll try to keep it. I've got a page break here, so try to keep it here, but y hat is going to be beta naught hat plus beta 1 hat x1 plus beta 2 hat x2 plus beta p hat xp. Okay. And we still build this model by minimizing the RSS, the residual sums of squares. Okay, so we still build this model, and maybe I will put it on a fresh page here. There. Haha. P predictors. The P's latched on. There. So we still move it to the next line here. We still build the model, or we still choose the estimates. We still choose estimates that minimize the RSS, which is the residual sums of squares. Okay. So, and I guess, sorry. What I should do is I should add a page here and then scoot this all down on a fresh page. I'll leave those there until I need them. Okay. So they're gonna get pulled down later and then I'll delete that page. Okay, so to interpret these slope coefficients, right, they're still coefficients, and we can still get the model, and we can still get R to do these calculations. And so that's not the concern, but we do have to interpret these. Now, because I have multiple coefficients here, right, how I interpret that is going to be slightly different. So it is the same, it's still the unit change that we expect to see in Y with a unit, it's the change in Y that we would expect to see with a unit change in X, but then we add on, assuming everything else is held constant. Okay, and so that's the difference, because we didn't have anything else to hold constant in the simple linear regression case. Okay. So in general, beta J is the jth coefficient. Okay. And maybe I'll say beta J hat, okay, is the average effect on Y of a 1 unit increase in xj. Okay, so this part is the same same interpretation as simple linear regression. Okay. But the new part is assuming that everything else is held constant. So holding all other predictors, and maybe I'll still use blue. I'll just highlight it. Too much pink. We'll reserve the pink for really important stuff. Holding all other predictors fixed. Okay, and I'll highlight that. That part's the new part. Okay, so that's really important. When you're interpreting these coefficients, then you have to mention that, okay, assuming everything else is held constant, then this coefficient would affect Y by this much, right, for each unit increase in xj. So we can talk about that the sales of, what was it? It was sales of something, and now I can't remember what the sales were, but yeah, it was something. But they were looking at marketing on TV, on radio, and in a newspaper, right? And so all of those categories have different budgets, right? You probably need a bigger budget for your TV ads than you do for your newspaper ads, for example, right? And so they have different budgets. And then what does playing around with those different budgets get you in terms of the predicted sales? So we already saw one model, right? And so what we can say here is, I'll just grab it. So we could consider individual models, right? So simple linear regressions with each individual predictor. So in this case, we're going to talk about predicting the sales using the TV budget, the radio budget, and the newspaper budget. Okay, so we could consider predicting sales from the advertising data. It's all coming back to me now. From the advertising data by building 3 individual simple linear regressions, 3 individual simple linear regressions. Oops. On the TV, radio, and newspaper budgets. Okay. So we already saw which one? Let's see, paste. We already saw a simple linear regression with TV as the predictor. Right, so we've already seen, and I'll delete all this here, clean this up. And maybe what I'll do is I'll make this a little bit easier to look at here. In section 3.1, we considered this model, which says that the predicted sales hat is 7.0325 plus 0.0475 times the TV. We also saw that both of these, the intercept and the slope, are both significant, right? So they're contributing in helping us predict sales. Now, one thing that I think I didn't mention yet, but I will now, is that sometimes the intercept will not be significant, but you do need some sort of anchor. And so you would just have the intercept there. It's possible to build a model without an intercept. As weird as that sounds, you can, but for interpretability, it's just easier if you have an intercept, right? So even if it's not contributing to the model, at least it's a jumping off point. Okay. Well, so we could do the same for radio and newspapers. So we've got these guys here. And maybe I'll just crop this up here. Okay. So here, what we're seeing, right, is that if we're predicting the sales still, sales hat is 9.312 plus 0.203 times the radio budget. And for this one, the predicted sales will be 12.351 plus 0.055 times the newspaper budget. Okay. And we notice that all of these p-values are really, really, really small. And so we see that each of these individually are contributing to the model, right? most coefficients except for the newspaper coefficient. That's the only one that's not less than 0.0005. It's still really small, 0.00115, right? And so most except the newspaper coefficients have p-values less than 0.00123. Okay. Which means that, but they all have p-values less than 0.05, which means that we conclude that they all contribute to predicting sales. And all p-values are less than alpha equal to 0.05, right? Which means that they are all contributing to predicting sales. Oops. Which means they all contribute on their own, right? Independently in predicting sales. But I'll just say in predicting sales. Okay. So I think I've got, what we can do is we can build a combined model. So now if we extend this to multiple linear regression, where we're not just looking at, different sales predictions for each budget, right? We want to look at, okay, what's the sales prediction if I spend this much on TV, this much on radio, and this much on the newspaper, for example, right? And so we combine these to predict sales by incorporating all three budgets. Okay. So what we're going to do is we're going to build a model that has sales, the predicted sales. It's going to have beta naught plus beta 1 times TV plus beta 2 times radio plus beta 3 times newspapers, or I'll just say newspaper. If I scoot this over, I'll have enough room. Newspaper plus some error term. Right? That's the population model, but that's okay. Right? What we're going to be looking is we want to estimate these coefficients. Right? So what we have is we're going to get some, oh, I forgot I brought them in already. Okay, good. So now we have some intercept and we have some coefficient on TV. Notice that it's different. It's going to be different. Oh, it's not. Seems weird. .046. Oh, it's slightly different. Just scroll around. Similar but slightly different. That makes sense, right? That they're not going to be the same coefficients because now I have some coefficients that are going to carry more of the weight in terms of being able to predict sales, right? We put them all in there to see how they all do in comparison to each other. And so now what we have is these are our coefficients. And then the next thing that we look at is, okay, I can build my model using the coefficients, but what can I do with these p-values? I see that I have a series of small p-values, And then now all of a sudden, it looks like the newspaper budget is not contributing to the sales at all. Okay, so you've got a decision to make here. You could remove it from the model completely, right? Or you could keep it in there because it is still happening. You're probably still working, sending ads to the newspaper. You understand that it doesn't do much, right? But in fact, it doesn't contribute to the sales or the predicted sales is what we're seeing. So, I mean, you could stop spending money on the newspaper, but we can keep it in there if we want to, but it's not significantly contributing to the model. So the newspaper budget does not contribute to predicting sales. Okay. And that's a change from before, right? We said, okay, well, it had the largest p-value, but it was still very small. So what's happening here, right? It's possible that the newspaper budget, right, was maybe intertwined with the TV and the radio budget, right? So if you increase the newspaper budget on its own, then the sales will increase. But that probably just means that you have larger budgets overall, right? So what we're seeing is that budget from the TV and potentially the radio, those are the ones that are carrying these predicted sales, right? And then, but when we just look at the sales and we look at the newspaper budgets, as the newspaper budget increases, then our sales will too, but it's not necessarily because of the newspaper budget increase, right? There's some variable in there that we haven't taken into account. Okay, so let's see here. All right, so our model here, the predicted sales is 2.939 plus 0.046 times the TV plus 0.189 times the radio minus 0.001 times the newspaper budget. Okay. So now what you can do is if you have some budget, and I think it's in thousands, so if you're spending 50,000 on TV advertising, then you would, I think it's in thousands, I can't remember, then you would put in 50 here, maybe 10 for the radio, and maybe, I don't know, 2,000 on the newspaper, something like that. And then we can predict the sales from here. How we interpret this 0.046 is for each unit increase in TV budget, right? We expect to see a 0.046 increase in the predicted sales, assuming the radio and the newspaper budgets stay the same or held steady. Okay. So to interpret this, for example, we expect a 0.046 increase in the predicted sales for each unit increase in TV budget, which I think was in thousands, right? And so that would be a $1,000 increase in the TV budget. You can just say unit increase in TV budget, assuming the radio budget and the newspaper budget are held steady, are fixed. Assuming the radio and newspaper budgets are held constant. So we can't allow, when we're interpreting these coefficients, we can't allow for things to be fluctuating all over the place. So that kind of makes sense. We need to focus on just the one coefficient. So it's assuming everything else is held steady. Okay. It doesn't matter what the radio is, what the radio budget is, and what the newspaper budget is, but they have to be steady. Okay, so the textbook asks these some important questions, which they then go on and answer in section 3.4. So that's really nice. It kind of fully in terms of this question, but I see I also have this correlation matrix, which I can talk about just briefly here. So we can look at the correlation between the variables, and that's going to help us explain why the newspaper was helping us predict the sales when it was just on its own, right? And so the newspaper has a pretty high correlation with the radio, and then the radio has a pretty high correlation with the sales. And so, and then of course the TV has a high correlation with the sales. So we expect it to be contributing to the model. That's fine. But then TV with the radio, there's very low correlation. So there's not a lot going on there. But then when we look at the radio and the newspaper, right, it seems that increasing the budget for the newspaper would also make it seem like it behaved the same way as if we increase the budget for the radio, or similar, right? And so that's why it's here. So this explains why newspaper was significant in the simple model. Okay. And it's because of its high correlation with the radio. Because of its high correlation with the radio. Nice. Okay. Huh. I keep thinking that they're somewhere else, but no, they're just above here, and that's confusing. Okay, so here, oh, cut. Here we have some of the questions that we could answer using regression or linear regression. Okay, and so here we have them in general. Okay, but then in section 3.4, these questions are answered specifically using the advertising data set. And I think just kind of for clarity, that would make more sense if you looked at that afterwards. But so here, these questions are answered in section 3.4 in relation to the advertising data. In relation to the advertising data, and I should capitalize it. Okay. But some of the few things that we could ask and wonder about is at least one of these predictors, right? If I have P predictors, useful in predicting the response. Okay. And so in general, we can do what we call an F test, right? Because we're used to seeing just one predictor, which is fine, because then we can just use the t-test and we can figure out if the slope is significant or not. Okay, but now we're going to work on the f-test. And so for question 1, or kind of that first bullet, let's say, we can test H naught. Beta 1 is equal to beta 2 is equal to beta p, which is equal to 0. This is the null hypothesis, is that nothing contributes to predicting y. None of these coefficients are significantly different from 0. Okay, so here this is saying none of the predictors help explain y. Okay. The opposite of that would be at least one helps us in predicting y, right? And so this is what we call the f-test, and you might have seen the ANOVA. I think you saw it briefly, right? But the ANOVA is how we check that. Okay, so then the alternative hypothesis here is going to be that at least one beta j is non-zero. Which would mean that it helps in predicting y. Okay, and so to test these hypotheses, we do an f-test using the ANOVA. We do an f-test, which is an ANOVA. And in general, you can reject if, or you can reject H naught. We're always stating our conclusion in terms of H naught, right? So in general, we can reject H naught if F is greater than 1. Okay, that's assuming that N is large. If N is large, right? Then you've got a pretty quick test to do, right? You just need the F statistic. Usually your R output would include the F statistic as well as the p-value for the F statistic, so you don't need to worry about it. Then you can just look at it. But in general, if F is larger than 1, then you have enough evidence to reject H naught. Okay. One thing that we are also kind of assuming here is that we don't allow for smaller sample sizes than we have predictors. Okay, so you can imagine if you have this tons and tons and tons of predictors on a small data set, that just seems weird, right? So the tools we have here can't handle that. Okay, we have to have more bigger sample sizes than we do predictors. So here, oops, we assume P is less than N, right? The number of predictors must be less than or fewer than the sample size. What's the proper word here? Fewer, I think. The sample size. Okay. Which I think you would probably react to anyways, and so it's not really a concern. But that is an assumption that we're making. Okay. So what's another thing we could check? Do all the predictors help to explain why, or is only a subset of the predictors useful, right? And so we can look at those p-values for each of the individual coefficients, right? We can employ model or variable selection, right? Which ones help me explain why? If you have a lot to choose from, right? Assuming you have a large data set, then you can use some variable selection techniques to pick the best predictors, okay? And so 2 is referring to variable selection. Okay. So for example, let's focus on the case where we only have 2 predictors, right? And so consider if P is just equal to 2, right? Then we can build 4 different models, 4 different linear models. We can build 4 different linear models. Can actually do more than that, but let's focus on these for now. Okay, so here I'll call it mod 1 is just no variables in there. Fair enough, but probably not one we're going to use. Mod 2 is maybe I just have x1. Mod 3, maybe I only have x2, or maybe mod 4, I have x1 plus x2. Maybe I should say and x2 because there's coefficients on there. So even though we would add them in our code, but I'll say and x2. Okay. And so here, in general, we would have 2 to the power of p different models, right? So here we had p equals 2. So I only have x1 and x2 to choose from here. But now imagine, even if you had 6 different predictors, that seems perfectly reasonable. Then you would have to consider 2 to the power of 6, so 64 different models, right? And so you don't want to map those all out. You want to have something that can run through and look at all of those for you. Potential models. Okay. So then we can use tools like backward selection, forward selection. We can use variable selection techniques to identify promising subsets of variables. To identify promising subsets of, I'll say predictors. They are variables, but I'll stick with the same terminology of predictors. But if you prefer to call them variables, that's fine too. Okay, so some of those techniques are listed here, and I did kind of cheat here. And I'll bring them down. And there was also a note here. Cut and delete. Okay, good. Oy. So the meat and potatoes is that there are different techniques for selecting these subsets. And of course, we have these kind of iterative methods that we can use. So first one is forward selection, meaning we begin with nothing in the model. And then, so we have an intercept, that's fine, but we don't have any predictors yet. And then what we do is we fit P simple linear regressions and add the ones that have the lowest residual sum of squares, okay? And then, so you would do them all individually, and then the one that has the lowest RSS, that one gets to be a predictor in your actual model. And then it goes through and it selects them in a forward way, in the sense that you start with nothing and then you're adding predictors as you move through, right? Until some stopping rule happens, right? So if the residual sum of squares is too large, then we stop adding these predictors in there, right? Or if we start adding variables that no longer have a significant coefficient, then we stop adding, right? And probably remove that last one. Okay. Whereas backward selection, we put all the predictors into the model, right? And then what we do is we slowly take away the least significant predictor at each iteration. Okay, and so at each step you remove the one with the largest p-value, and I couldn't find it in here, but for some reason I have it in my head because my supervisor used to say it all the time, but I'm pretty sure, and maybe R has been, is more sophisticated now and it just does it, but I'm pretty sure you're supposed to bump it to the bottom of the predictors list before you remove it. Okay. But I think maybe R just knows what to do now, so that's fine. And they don't talk about it, so it's nothing you have to worry about, but I was looking for it and I couldn't find it, so maybe it's not an issue anymore. Or we can do a combination, right? Where we kind of, we start with no variables, and then we can add some variables, and then if we want to remove some variables because the p-value is too large, then we can move back and forth. Okay, so that would be a mixed selection. And one note, whoops. Is that backward selection, you can't use it if P is greater than N. So remember, everything that we're doing assumes that you have fewer predictors than you do sample size, right? And so, but backward selection just really cannot be used if that's the case, okay? So forward selection, you can always use, but things get weird when you have tons and tons of predictors. And so, oh yeah, so kind of the trade-off, the mixed selection, is because the forward selection, it goes through and it basically picks, imagine a TV scenario, you're picking a team for your sports. I don't know, that never happened in my life, but maybe it's a real thing, but I don't think so. Where, you're picking your team and, oh, I want this person on my team and I want this person on my team. And then so that's forward selection, right? Forward selection goes through which one of you has the best RSS, and then it picks that one. Okay, you're on my team. Okay, who's next? You're on my team. You're on my team. But what happens, what we saw, right, is in the newspaper case, we saw that, okay, on its own, right, it was doing a reasonable job. But then when we incorporated it with the other variables, all of a sudden it wasn't significant anymore. So then if we just have forward selection, then all those kind of redundant variables would still be in the model. But if we do a mixed selection, then we are able to always look in and say, hey, is there anyone here who's not contributing to the model? If so, get out, right? And that's backward selection. And then forward selection goes and picks their team, and then the backward selection basically puts them back, right? Maybe it's like, I don't know, shopping with a kid, they put stuff in your cart and then you go put it back, right? Some stuff, yeah, okay, good idea. Most of the stuff you put back. Right? So that's mixed selection. Okay, so let's see here. Referring to these questions again, right? So we can use variable selection to pick different subsets that help explain why. Now, what's interesting is backward selection and forward selection don't necessarily end up at the same model, okay? Often they will, but not necessarily. So I do want to add that as a note here. The different variable selection techniques or variable selection methods often yield slightly different models. Often yield slightly different models. Yeah. So then that leads us to the next kind of important question. Well, how do I pick a model here? Which one do I choose? So we've got, maybe we've got a forward selection model, maybe we've got a backward selection, maybe we've got a mixed selection, who knows? So question 3 is on model fit, right? It's regarding model fit. We've seen R squared, for example, in simple linear regression, and we can still use R squared. It's just how we calculate it is just slightly different. So we can still use R squared as a measure of model performance, but in multiple regression, linear regression, I'll say R squared is the correlation between Y and the predicted values of Y. Oops. Make this look like an R. Okay. There are other methods that we could use. There's Mallow's CP, which I can't remember what it measures. I can't remember, but there's the AIC, the BIC, the adjusted R squared, and so some other measures include Mallow's CP, the AIC, the BIC, the Akiki information criterion, and the Bayesian information criterion, and the adjusted R squared. Okay, we're not going to use these, so I'm going to parking lot those, right? But just know that there are other measures than just the R squared that we could look at. Okay, good. And then finally, the last question here that we could be interested in or could answer with regression is, if I have a set of predictor values, what response value should we predict and how accurate is our prediction? So for an individual set of predictor values, we can we can find a prediction of y hat, right, just by substituting in those values of x, x1, x2, x3, right? But we can also build prediction intervals, but those are for one observation. We can build confidence intervals, but that's for the mean observation. So those are slightly different. So for the fourth question, we want to do predictions. We plug in the values of x1, x2, up to xp into our model, right? Whatever is relevant into our model and calculate y hat. Yeah. We can also build prediction intervals and confidence intervals, but I'll put that in brackets. We could also build prediction intervals and or confidence intervals. Yeah. Let's see where this page break is. Not for a while. Okay. 3.3 lists some other considerations. One main thing that we haven't talked about yet is what if I have categorical predictors, right? So the main one is if I have categorical predictors. Which we often call factors. If we have two levels in a factor, okay, busting out some new terminology here, but they're just categorical predictors, right? So if we have two levels, we use dummy variables. And you may or may not have heard of dummy variables before. It's just a 0, 1 variable. Dummy variables. I actually think it's really cute. They've got a little note here. In machine learning, I guess they didn't like the term dummy variables, and so they decided to call it one-hot encoding, which makes more sense actually than dummy variables. So in machine learning, they call them one-hot encoding. Okay. So in general, right, xi is going to be 1 or 0, right? So a dummy variable looks like this. And here, this is basically when it's on and when it's off. Okay, so it's like an on-off switch. So you're multiplying by 1 if it's on, and you're multiplying by 0 if it's off, which removes that coefficient from your predicted value of y, right? But besides that, nothing really changes. In most scenarios, you can boil down to a binary situation. So this is a 1-0 situation is called a binary situation. And so most categorical variables, pretty well all, right? Most categorical variables can be boiled down into a dummy variable, right? One or more dummy variables is what we tend to use. So if we have more categories, more than one category that we're truly interested in, then we would have more than one dummy variables. So into one or more dummy variables. Okay. So for example, if you think about your grade, let's say you can get an A, or you can get a B, or you can get a C. Let's just look at those, no. Okay, so here are our categories. So here we have 4 levels. If we were only concerned with A's, right? Getting an A, so the student got A's or they didn't, right? So if we're only concerned with an A grade, then the others could be as just lumped into zeros, right? They're not A's. So if we only care about an A grade, then what we would have is 1 if an A, and 0 if not an A, which would be B, C's, or F's. Of course, we have more layers than that, but so then Xi would be 1 if it's an A, and then 0 if it's not an A, right? If we cared about the other categories as well, right? What happens if they got a B? What happens if they got a C? What happens if they got an F, right? Then we would have to make K minus 1 dummy variables, right? Where K is the number of levels. So if we care about each of the K levels, we would need to create K minus 1 dummy variables. Okay. So you would have maybe X1 is 1 if it's an A, 0 if not A. X2, 1 if it's a B, 0 if not B. And then X3 would be 1 if a C and 0 if not C. And then what happens, why do we only need K minus 1 dummy variables? Well, because if A is, hey, we're on the same page here. So if all of these are off, then that would be our remaining option, okay? Which is basically going to be our intercept. Okay, so if X1 equals 0 and X2 equals 0 and X3 equals 0, then we know that we're in the remaining category, which is an F. Then we know we are in the remaining category, which is an F. Okay. So what happens is you're going to have some Y hat plus beta naught hat plus beta 1 hat X1 plus beta 2 hat X2 plus beta 3 hat X3. So this beta naught hat is actually the prediction for if you're in the F category, right? So that's your jumping off point. Prediction for the F category. Because X1 would be 0, X2 would be 0, and X3 would be 0. But if X1 is 1, right, then I turn on X1, but X2 and X3 are still turned off. So if X1 is 1, then what we get is we get Y hat is beta naught hat plus beta 1 hat X1 plus 0 plus 0. Okay. So it means that, and this value is just 1, so then Y hat is beta naught hat plus beta 1 hat times 1, right? So beta 1 hat is the prediction, the added value of being in group 1. So beta 1 hat is the added value of being in group 1. So an A student over being in group 0 or in the F group. If X1, then because we use the F group as a starting point. So then what happens is the beta 1 hat is, okay, so if you're in the F group, you're at the beta naught hat, okay? But then what we say is, okay, if you're in the A group, then yeah, you started here at the F group, but then you're added on to that group. So with my last minute, I'll show you with some numbers, and it's actually really fun. So so beta 1 hat is the added value of being in group 1, so an A student over being at the intercept, which in this case is an F student. So if you have your predicted grade seems reasonable is, you know, maybe 40 plus, let's say, I don't want to do 60, maybe 55 times X1 plus 30 times X2 plus 20 times X3. Okay. So then if you're an F student, the predicted grade is 40. If you're an A student, right, because here you're an A student, your predicted grade is 40 plus 55. Awesome. And then here you're a B student, but you can't be both at the same time. So that's why that's why the one hot is really kind of a cute term. Awesome. Hey, that's great. And it looks like I'm all out of time, so that's great. But pretty fun stuff. So if you have any questions, let me know. Otherwise, I'll stop this recording here.